For this question, if you look at what they're asking you is what time was the car stopped? Well, the car is stopped when the velocity is 0. It's not moving. So, in terms of the graph, we got to find out where the velocity is 0, and besides the very, very initial moments, this part in time right there is when the car is stopped, and so I'm going to say from times 0.7 to 0.8 hours is when this car is stopped. Its velocity is 0. Has the greatest velocity. We're looking for the point on the graph where it's the highest up because it tells us what velocity it is. And so this is the highest point on the graph, and in terms of its time, we got times of 0.2 to 0.4 hours. And so 0.2, 0.4 hours is when our velocity is the highest on a velocity and time graph. Look for the highest spot. What was the greatest velocity? Again, look at the very top. See what that part tells you on the graph, and let's look over now. What is that velocity? That is 60.0 kilometers per hour. So what was the greatest velocity? It was 60 kilometers per hour. When was this car accelerating? And accelerating just means when are you changing speed? Remember, acceleration is equal to the change in velocity over a change in time. Well, when you do that, we shall look on this graph. Where does this graph have a changing velocity? Well, in the beginning it does, later in the middle it does, and a little bit later in the middle it does too. It's actually a lot of portions of time where the velocity is not the same. It's always changing throughout those sloped portions. So whenever you have a slope on a velocity and time graph, that tells you the acceleration. So in terms of this guy, there's 3 answers. You can go from 0 to 0.2 hours. Also, from 0.4 to 0.7 hours, and also from 0.8, oh, I'm so sorry, that looks sloppy, to 1.0 hours. Alright, how fast was this car going at 1 hour? Well, this is where 1 hour is, and at that point in time, it has this velocity. I'm going to trace all the way over. That is 40 kilometers per hour. So this is just reading the graph. Well, I know the time. I can find the velocity now. What is the acceleration at 0.9 hours? Well, at 0.9 hours, we're right here, and oh, I only have a dot there. Well, you know what? What's nice about this graph is that it's a velocity and time graph. And if it's a velocity and time graph, if I find the slope of the line on this graph, that tells me the acceleration. So what I could do is find the slope of this portion of that line, and so let's pick out 2 points. I'm going to try and make this as easy as I can. So there's one spot at 0.8 hours, and the velocity is 0, very top. We got a time of 1 hour, and the velocity is at 40. So in terms of the work here, the slope of that line again is your acceleration, so I know the acceleration is a change in velocity over change in time. And so what I know is that my change in velocity, it's going to a final velocity 40. And I'm going to skip units just for the sake of being neat on my work here. Minus 0 divided by a time of 1.0 minus 0.8. When I do that, I end up with a huge acceleration of 200 kilometers per hour squared. So don't forget the 2 there. My 2 is super sloppy, but it should be kilometers per hour squared. So in terms of question number 2, it's asking us, hey, we got 2 cars. Plot the points on the graph, which we did. So we got car A in blue and car B in red. And in terms of finding the actual velocity of each car, what we need to do is find the slope of this line. And what we know is that the slope of these 2 lines, it tells us the velocity of each car. So for car A, we picked 2 points, and those 2 points, if you can't see them, one's down here, and the other one is up there. And when we solve for the velocity, it's a change in displacement over a change in time, we get about 1 kilometer per minute. Car B, same idea. We're going to pick 2 points, so there's 1 point down there, 1 point up here. And when you plug in 2's values in terms of the change in displacement over time, we get about 0.75 kilometers per minute compared to 1 kilometer per minute. And what's nice to know about this graph is, well, just by looking at the graph, you can figure out which car is going faster. If you have a steeper slope, you are going faster. And so the blue line is a steeper slope. And it makes sense. The blue car is going 1.1 kilometers per minute, which is faster than our 0.75 kilometers per minute. Drawing a velocity and time graph for this situation when you got a ball thrown up in the air, VT. I'm going to say that down is negative, and so you got to pick which one's negative for you. It's up negative, up positive, down positive. But for me, I'm going to say that down is negative, and so if I throw a ball up in the air, in the beginning it's going up, up, and up, and up, and so as it's going up, it starts off with some initial velocity, and at the very top of its motion, it has no velocity. It has a velocity of 0 for a moment in time. And as it reaches the top, it comes back down to the ground. If it's coming back down to the ground, again, I'm calling down as being the negative direction. So that's true. It's coming down faster and faster and faster. It's getting faster in the negative direction. It's getting a larger negative velocity. So in terms of my graph, there's my line. It is actually a straight line going downwards. And what's nice to know is that, well, if I think about what's going on, this is weird that it's going up and down in terms of its displacement. But the velocity and time graph looks like a straight line. Well, that should be nice because I know that the line and the slope of a velocity and time graph is the acceleration. Slope of VT graph. And if this is on Earth, I actually know what that slope's going to be numerically. We're going to say that that's going to be about negative 10 meters per second squared. That is the acceleration due to gravity. That's what is accelerating this ball as it goes up and down. It is changing its velocity 10 meters per second every single second in the downward direction. Alright, I'm going to try and describe what's going on with this last question here. We got a police car and also a truck. And so with these two things, a police car and a truck, what we know in question 4 is that this truck is traveling at a constant velocity of 28 meters per second. And so I can kind of get some values written out there. For the cop, he's accelerating from rest at 4 meters per second squared. So what this question is asking us is how many seconds will it take for this cop car to catch the truck? And so I'm looking for a time which is similar to both vehicles, the cop car and the truck. And what I also know is when they meet, they're at the same spot, which means their displacements are at the same location. So that's why in the beginning we can state that the displacements of the truck and the cop are equal because they need to be at the same spot for them to be meeting together. And at that spot they'll have the same time as well too. And so for the truck, what I know is that, you know what, he's at a constant velocity. And so to describe his displacement over a period of time, we're going to say the velocity of the truck times the time is where this truck is. For the cop, it's a different story. He's accelerating from rest, and so his displacement is described by 1/2 acceleration times time squared. So I'm going to do a little bit of algebra now and kind of get rid of some stuff to simplify this. Get rid of that time value, get rid of that squared. So now we can simplify this to just the velocity of the truck is equal to the 1/2 acceleration of the cop times the time. And again, this is where they are meeting in the same location at the same time. So when I solve for time, I do a little bit of rearranging. I end up with an equation saying 2 times the velocity of the truck divided by the acceleration of the cop. That is the time. And plug in the values now. The truck's velocity was 28 meters per second. Cop's acceleration was 4 meters per second squared. And units work out. Math works out. Our time becomes 14 seconds. And you can also do this by actually graphing this on the actual graph given and figure out the area under the graph when those two areas are the same. And the reason why is because we know that for a velocity and time graph, the area under a curve, oh, that's really sloppy, I'm sorry, that equals your displacement or where you are. So again, you can graph these two different objects out and find where those two areas are equal to each other, and that is your displacement. We can also solve for what time that's going to be. All right.